In this video, we're going to talk about floating points. So when we are dealing with solving a problem, more often than not, we need to deal with real numbers, 10.55 or whatever else. So the question is, how is this number stored in computers? One interesting thing is that if you were asking this question before 1985, then the answer would be many different ways. But post 1985, all the computer vendors, people who build computer and design computer, write programs, got together and they agreed on a standard of how a real number will be represented, and they call it floating point standards, IEEE, which is an institute which does standards, and then they gave it a number 754. So starting in 1985 and beyond, all numbers, real numbers, are being represented using the standards. So they come in a single precision and it comes in double precision. All it is the amount of precision you get is more in double precision. The drawback being that it would require more space to do that. Okay, so let's go ahead and take a look at this standard and then hopefully put it to use. A single precision is going to be organized in 4 bytes. And these are the bit numbers in here. So bit 0 to bit 22 is referred to as fraction. A lot of time we use F's to represent it, F. And then they call this exponent, but that's a little bit of a misnomer. It's actually the real exponent to the powers of 2 plus 127 is what is stored in here, and then 127 is referred to as a bias. And then the most significant bit, 31, is a sign where a s equal to 0 refer to positive numbers, and a 1 in this bit requires negative numbers. Okay, so that tells us it's a plus or minus number. And then this bias, the way they have saved it, the exponent, they don't have to worry about telling you whether it's plus or minus. The scheme will automatically show it, because if what the number saved in here is above 127, then it's going to be a positive component. If it's less than 127, the number that is in here, then your exponent is going to be negative numbers. And we're going to do some practice here just to make sure we understand. Let's say someone comes to us and gives us they'll say this variable is declared as a single precision floating point, and when you look in the memory, let's say there are 4 locations. Let me get it a little bit bigger so I can. So if we look in the memory and assume the content is hex, and let's say this starts at location 80, and as looking at this thing, we know there is 4 bytes. This will take 4 bytes to store. So byte 1, byte 2, byte 3, byte 4. Here we're going to have the least significant byte, the next more significant byte, then let's say more significant byte here, and then C0 here. This is how, so you start from the least significant byte to the most significant byte. So the number they're asking, and this is a data address, right? So, and these are all, let's assume, in hex, which makes it a lot easier to work with. Which basically means the number we are being asked to convert, if it's fully written out, it would be C0, E0, 0, 0, 0, 0. Okay, now let's go ahead and see what the bits are here. If you start breaking this up, C is 1, 1, 0, 0, and then 0 is 1, 2, 3, 4, E is 1, 1, 1, 0, and the rest of this thing is 0. So if I've done my job right, this is a C, this is a 0, and this is an E, and the rest are 0. So now let's go ahead and see what number does this floating point number in decimal shows. So in decimal, it will tell us that it's a 1, so it's a negative number. Let me use a different color. So it's 1. That 1 tells us is a negative number. The exponents, if you look at the exponent, this is the exponent. See that? This 8 bits. So if you look at this 8-bit, you've got 128 here and 1 here. So the exponent is 1 plus bias is 128 is equal to, I'm sorry, to 129, because 128 plus a 1. 129 is the exponent plus 127, which basically will tell us that the exponents of 2 is going to be 129 minus 127, so it's a 2. Okay? And then the next item is, do you always have a 1? This 1 is always there, whether we don't show that portion of it. And these are all the fractions that are available. All the fractions are 1, 1 times 2 to the 2. So that's basically how you go from a hexadecimal representing, or bytes in the memory representing a float, to what the decimal value of this is. So another way to think about it, every time you multiply by 2, one of these moves over, the decimal point moves over to the right. So since I have 2, what's going to happen, this is actually 1, 1, 1. Remember, these whole thing, at least this number, is in base 2. So 1, 1, 1 in base 2. So this is really a minus 7. This was a way of representing minus 7. Okay, so now that we have a little understanding of how you take a number given to you and try to figure out this a single precision floating point number and ask you how to do the decimal number, we did that. Now let's go ahead, and someone gives us a opposite of that. They'll give us a decimal number, 21.375, and they ask us what is the single precision floating point equivalent. So first of all, what we can do is say it's a positive number. So that basically tells us that the sign is equal to 0. Then we have to convert this to its binary equivalent. So go to binary equivalent. So if I go to a binary equivalent, how would I do that? Well, we're going to use the method we learned a little while ago. So I will find the highest power of 2 that is subtractable from here, and the highest power of 2 that I know of is that can subtract from here is 2 to the 4, because that's 16. 16 I can subtract from there, and if I do that, I'm going to get a 5.375. Since I can subtract it, then I get a 1 in here. Then I got 5.375, but that's not subtractable from 8, which is 2 to the power of 3, so I get a 0 in here. But it's subtractable from 2 to the power of 2, which is 4, and the result is 1.375, so that's a 1. and it cannot be subtracted from 2 to the power of 1, so I'll put a 0 in here. But it can be subtracted from 2 to the power of 0, which is 1. So 1.375, you subtract that from there, and you get a 0.375, and that's a 1. Now, period, because you're going from 0 to minus 1. 2 to the minus 1 is half, but you can't subtract half from 3.75, so that's a 0. Okay? Now, moving on, this 2 to the power of minus 2 is actually 0.25, and that I can subtract from 0.375. If I subtract 2 to the minus 2, which is 1/4 from that, or 0.25 from there. I would get 0.125 as a remainder, and I get remainder, and I get a 1. So 2 to the power of minus 3 happened to be 1/8 and happened to be 0.125. So if you subtract these from each other, you're going to get a 0, and you're done. So the number you have looks like this. But in order for me to go to a single precision, I have to move this decimal point all the way here, because the format of all numbers should be 1 point something. So 0, 1, 0, 1, 0, 1, which means this number is actually moved the decimal point. So I get, in order for me to make sure this number is the same, I have to put a power in here to push it back to where it was. Is 1 place, 2 place, 3 place, 4 place. So this is 2 to the power of 4. Okay, so that's a number. Now I can go off and say, okay, here are the fractions. So I'll start, and then this is the exponent. So the plus sign gives me a 0 for the sign. For the exponent plus bias, which is 127, would be 127 plus 4, which is 131. And 131, if I write it, it would be 128, 0, 0, 0, 0, 0, 1, 1. So 128 plus 3 gives me the number I'm looking for, which is, so this is 4. Therefore, the number I will need to put in here is 131. All right, the next step is to figure out what to do with this fraction. So since this is this part is the exponent plus 127, the next thing I need is all the fractions I have. Remember, we do not write this one. This one is implied. So it's going to be 0, 1, 0, 1, 0, 1 as the answer. So this, and then the rest of the bets for the floating point will be 0. So this would be bet 0. This would be bet 22. This would be 23. This would be 30, and this would be 31, and there we have it. If you want to, if most of the time you're asked to write this in the hex form, so the float, single precision float of the number here in hex would be, basically you start from this side, 4, 4, 4, 4. So the answer would be 0x, the single floating point equivalent of the number we had, which was 21.375, will be 0, 4, 1, A, 0, 0, 0, 0. But remember, it's 32 bits, so it's got to have at least, oops, did I get enough? Oh, some more zeros we'll have to throw in. Because it's got to be 4 bytes, so maybe I went too much. Here is 1, 2, 3, 4. Actually, it was fine. Didn't need this last one. So here's my 4 byte of single floating point. Okay, now let's change over and say, let's say this just wasn't big enough, wasn't accurate enough. You can always go to double precision. And if you look at double precision, the format is identical to the other one. You have your fraction bits all spread out here, and you have your exponents plus, again, remember, exponent plus a bias goes in here. So this is basically what this is in here is exponent plus 1023. For the double precision is a little bit bigger. Sign bits still exactly the same as before, and these are all the fractions here. And as you can notice, you get a lot more fractions, so you can be more precise, and you get a lot more power. But let's go ahead and take this number. This number is still going to be the same. So if I take this number and want to write it in 2's complement in a double precision, so this was 21.375. we turned that into a binary number, and the binary number was 1.01. Let me write this out. 1.01. Should make it a little smaller so I can see it. No point. 0.10101 times 2 to the power of 4. So that was the conversion to a binary equivalent of this number in decimal. So what would be the double precision? So 4 so the sign is basically plus. Sign is a plus. And then, so what the exponent would be basically 4. The exponent would be 4 plus 1023, which will be 1027. Okay, so if we do this, just because the sign is plus, then we're going to put a 0 in here, and then for the piece for sign plus bias, which is 1023, all I have to do is say, okay, this is 1024, 0, 0, 0, 0. So I've got 4 in here. So this number is 127 if I did it right. So you got 124 here, and you got 3 in here, so that gives us 127. Next, I got to write all the fractions. The fractions, remember, we do not, this one is implied, so we only write this piece of it. So it's going to be 0, 1, 0, 1, 0, 1. And so the rest of the bits all the way to 0, they're all going to be zeros. So if I were to write this in the hex format, I would have a 4, 0, 6, A, 8, and all that. So if I were to write it, would be 0x, 4, 0, 6, A, 1, 0, A1, another one, A, 8. So we've got 1 byte, 2 byte, 3 byte, 4, 5, 6, 7, 8. So I should have 8 bytes in here. 1, 2, 3, 1, 2, 3, 4, 5. Well, we got to do a few more. So I've got, I need to work on my counting. Let's go back and recount. Here's 1 byte, 2 byte, 3, 4, 5, 6, 7, 8. This is the right representation of a double precision floating point representation of 21.375 in decimal. Now, there are some interesting things we can talk about, such as what is the largest possible number, what's the smallest possible numbers, and that would be a good piece of information to talk about. There are certain numbers formats in this combination that is kept simply to be able to represent infinite, 0, and all that. So we'll let's go ahead and take. Here are some special cases. If you ever see that exponent 0 fraction is 0, that is artificially called a 0. In reality, as you know, that's not 0. But if exponent 0 and fraction is 0, that's a special case. It kept and indicates 0. Normal numbers will have, non-zero either going to have non-zero fraction, or they're going to have non-zero exponent, one of those two. A couple of things is when the maximum is used, 255 is the maximum number you can put in the exponent plus bias portion of the single precision, and then 2047 is the maximum you can put in the double precision and the double precision exponent plus bias. And if that case happened, this is just an indication that this is not a real numbers, okay? And if your fractions happen to be 0, then that's an indication of an infinity, representation of infinity in the computers. Other than that, then it will be normal numbers, okay? That brings us to the end of this overview or presentation of single precision and double precision.